40th lecture, we continue our discussion of digital circuits. In contrast to analysis, logic circuit synthesis means devising a circuit to perform a given logic function. For example, when you want to add two binary numbers, two bits, let's say A and B, well, we know if 0, now it is addition. We know if we add 0 and 0, it's not an OR operation, okay? When we add, well, how do I represent this? A added to B, 0 and 0, the result is 0. When you add 0 and 1, the result is 1. When you add 1 and 0, once again the result is 1. But when you add 1 and 1, 1, 0. So the sum is 0, and this one is a carry. And therefore, in general, I would require a sum and a carry. When you add two bits, two binary digits, then we require a sum, and we cannot express the result by one bit. We require two bits. One of them is the sum and the other is the carry. The carry is 1 only in the fourth case. In all other cases, the carry is 0. We want to make a digital circuit for this purpose, and such a digital circuit is obviously, for obvious reasons, it's called an adder. It is also given an adjective of half adder, because it does not consider the carry of the previous bit addition. This addition may be at a certain place in the addition. For example, 1 1 1 0 0 1 1 1. Now, if I add these two, I get a sum of 0 and a carry of 1, but the carry of the previous addition is not taken care of. So this is called half adder, and you can appreciate that one half adder will be needed in the addition of any two binary numbers. The first digit, the rightmost digit addition, shall require a half adder, because you don't have a carry. You don't have a carry from the previous addition, because there is no previous addition. On the other hand, if you want to add any two bits in between, you shall require a full adder. An adder in which the carry of the previous addition is also accounted for is called a full adder. First, let us look at a half adder. In a half adder, this is the logic. There are two outputs, a sum and carry, and there are two inputs, A and B. How do you represent S and C? That is the question. And you can verify that in such situations, you have to consider only the outputs which are 1. That is, you consider only this output and this output, and then write S as, in terms of A and B. A is 0 here, so A is not true, so you write A bar, and then B is 1, so B, or either this or A B bar. This is the sum. Is the point clear? It can be easily verified that this truth table S, A and B is represented by this expression, and the simplified method, this is true for all, this is valid in all situations. Simplified method is, you look at those rows in which the output is 1. You look at only those rows in which the output is 1. and take the AND operation of the variables. Wherever the variable is 1, take the variable as it is. Wherever the variable is 0, take the variable in a complemented form. This is always true. For example, for writing C, we have only to consider this row, and in this row you see A and B both are 1, therefore C is simply equal to AB. Now, if I represent this half adder logic, I rewrite the half adder logic A bar B plus A B bar. I should say or A bar and B or A and B bar. Well, I will simplify this in terms of ordinary language. C is simply AB. Then all that I have to do is I have to use a NOT gate for A, and then have a B, have an AND gate. This is A bar B. Similarly, I have to have an A and B with a NOT gate, another AND gate, and these two outputs are to be ORed. Therefore, I require another OR gate. And this is S. C, as you see, is simply AB, and therefore what I require is another AND gate, and this is C equal to AB. How many gates are we needing? 1, 2, 3, 4, 5, 6. All right. This is the simple synthesis, starting from this simple-minded synthesis. Well, in synthesis also, one asks the question, can you get a simpler form? Can you get a simpler form? Well, a simpler form is possible, as we shall see now. Simpler form is possible. Our S is A bar B plus A B bar, and I can write this with two inversions. This is same. Any variable with two inversions is the same, and therefore S I have written with two inversions. All right. Now, with one inversion, I apply De Morgan's theorem, that is A bar B inversion and A B bar inversion, and the whole thing inverted again. All right. A bar B inversion, this OR becomes AND, and A B bar inversion. Is this step clear? Is this step clear? Okay. So inversion remains. Now I expand this. I get A or B bar by De Morgan's theorem, and the operation is converted to OR with inversion, and what do I get here? A bar plus B. Now, if I simplify this, A bar is 0 and B bar is 0. So, what I get is AB or A bar B bar. I can also write this as now I take this inversion out, AB bar and A or B. Can I write like this? Okay. AB bar and A bar B bar whole bar. Can I write like this, A or B and AB bar? Yes? Okay. Now let us see how this expression can be represented by another logic circuit. S equals A or B and AB inverted. You see, I have A and B. I have an OR gate, so this is A or B. Then I have A and B. Then a NOT, or I could combine the two. All right, let's take an AND. then this is AB bar, then and therefore either way it's okay. We have to use another NAND to be able to get AB, which is equal to C. Alright. Now I take this and then AND. So it is S. How many gates have I used? 1, 2, 3, 4. Instead of how many did we use earlier? 7. Alright. So this is less costly than the previous circuit. This expression S equal to A bar B or AB bar, which is the logical expression for the sum digit, for the sum bit, is also considered as an operation, and this operation is defined as definition an exclusive OR operation. That is A, or if it is exclusive OR, then you put a circle around it, B, and this operation is called exclusive OR operation, exclusive OR. Sometimes in the world of abbreviations is also called XOR, XOR operation. XOR is exclusive OR operation. Alright, and there are manufacturers make gates which are exclusive OR gates. To look at this further, since this is an important operation, exclusive OR is A, exclusive OR B is A bar B plus AB bar. Alright, if I write the truth table A, B and S, well, the truth table is the same as that of the sum bit. 0, 0 is 0, 0, 1 is 1, 1, 0 is 0, and 1, 1, 0 is 1, and 1, 1 is 0. This is the only thing that it differs from the OR gate, isn't it? This is the only row in which the output differs from the OR gate. This is why it's called an exclusive OR. You can also see, follow this carefully, you can also see that the output of this exclusive OR gate is 1 only when the two inputs are dissimilar, and therefore an exclusive OR is also called an inequality detector. Inequality detector, that is, when the two inputs are unequal, then the output shall be 1. This is called an inequality detector, and exclusive OR has many applications. The simple gate has many applications. The circuit symbol for an exclusive OR is exactly like that of an OR, except that another curve is included here, another similar curve. Okay, what we do is two inputs, then instead of drawing the simple OR, we make this double line. Don't ask me why this symbol, why not something else. This was universally adopted convention now, but it originated basically with the inventors of digital circuits, exclusive OR. So in terms of an exclusive OR, you see the half adder circuit is simply A, B. You can do it only two gates. One is the exclusive OR, which gives you the sum, and the other is NAND. AND, okay. This is C. This is A bar B plus A B bar. Question: can a NAND gate, can a number of NAND gates be connected to make an exclusive OR? Yes. Can a number of NOR gates be connected to make exclusive OR? If we manufacture only exclusive OR, can we get all other gates? Why not? If we manufacture only exclusive OR gates, A company decides to manufacture only exclusive OR, and then you, in your circuit design, you require AND gates, you require OR gates, you require NOT. That is the inability. So exclusive OR is therefore not a universal gate. Now I am introducing another term, universal. Universal gates are only these two, NAND and NOR. Universal gates are those with the help of which all other gates can be synthesized. Exclusive OR does not qualify in that category. Now let's look at a full adder. A full adder, as I had said, requires to add three things: the given 2 digits, given 2 bits, and the carry of the previous. And therefore we shall require 2 half adders, because one half adder can add only 2 bits, and therefore we shall require 2 half adders. Let's say half adder 1 and half adder 2. Suppose I want to add, let's say, A and B, two bits A and B. The result would be sum and carry. This is a half adder. Now the sum comes to the next half adder and adds to the carry of the previous addition. The result would be, I'll tell you what to do with this. Where would this carry go? To the next left addition point. All right. So this carry will go to the next left addition point, and then this would be a sum, and this would be carry. What do I do with this? This would go to, okay, an OR operation. This is the carry that goes to the left, to the next addition. Let me illustrate this. The best way to show that it is correct is to illustrate. Let me take two numbers, 1 0 1 1, 1 1 1 0. We represent the sum here and the carry here. Okay. 1 and 0, the sum is 1 and the carry is 0. This carry goes to the next, all right, next bit. All right. 1 and 1 is 0 and the carry is 1. It goes here. This carry had no effect because it is a 0. Now you have 0 and 1 is 1. This carry then goes to the next one. Or another way of looking at this is 1 plus 0 is 1. 1 plus 1 is 1 0. Oh, I beg your pardon. This would be 0 and 1 goes here. Now we have the general situation in which the 2 bits are 1 1 and the carry is also 1. Okay. What would be the result here? This is 1 0 1 1. So 1 and another carry 1. So this would be 1. Agreed? Now let's represent this here. A is 1, B is 1. Okay. So the sum is 0 and the carry is 1. The previous carry was 1. So the sum and carry, this is, S is now 1 and C is now 0. So 0 or 1, this is 1, 1 comes in. You can show that this is a full adder circuit for any situation. And this is the most general situation where all the 3 are 1. Otherwise, you will get trivial things. But an OR operation is needed here, not AND. Suppose this carry was 1, this carry was 1. Then this carry would have been, if it was not OR, if it was an AND, this would have been Oh, so we can do it and also because if this is 1 and 0, this is and this will be 0. So you require an OR. You can show that this is the circuit. Therefore, if I have, let's say, a 4-bit number to be added to another 4-bit number, let's say I have A4, A3, A2, A1, B1, B2, B3, B4. All right. How many half adders shall we need? Just one? Half adder. Half adder is required only for this, only for the first column. For the others I require how many? Obviously 3. 3 full adders. So I require 1 half adder and 3 full adders. All right. The result would be sum 1, sum 2, sum 3, sum 4 and carry of the 4th. Yes. Yeah. Same full adder. Oh, there will be a race. It would not know when to stop. There would be a race. No, such things are dangerous in digital circuits. In fact, sometimes they occur without your wanting it, because there are delays in the circuit, and then you have terrible problems, very serious problems. There are terms like rat race and things like that. Okay, so we know what is a full adder. Finally, we'll look at a specific design example, and that's how we shall conclude this class. And this design example is, there are 3 people in, let's say, a board of a company. There are 3 people, and a motion will be passed when majority of them say yes. Majority means 2. All right, majority is 2, or it can also be 3. All right, this is a very simple situation. We want to make a digital circuit to represent this. Such a situation is called a voting situation, a vote-taking situation. Obviously, it's a vote-taking situation. Let these 3 people in the board be A, B, and C, and let the decision be F. All right. Therefore, if A, B, and C are all the 3 0, the decision is 0. Okay. If 0, 0, 1, then the decision is 0. If it is 0, 1, 0, you see that I am increasing by 1. It is 0. 0, 1, 1, it is 1. 1, 0, 0, it is 0. 1, 0, 1, it is 1. 1, 1, 0, it is 1. Finally, 1, 1, 1, it is 1. How many? 1, 2, 3, 4, 5, 6, 7, 8. Okay, I am done. Now, what I want to do is, I want to write an expression for F, a logical expression. And as I had said, all that you have to do is to look at the ones in which the results are 1, and OR them. That is, you write the logical expressions corresponding to this. This, for example, this row will represent A bar, B, C. Wherever there is a 0, you take the complement. Wherever there is a 1, you take the variable. And therefore, my F shall be equal to A bar B C plus, which means an OR. The next is A B bar C. The next is A B C bar, and the 4th one is A B C. Now, I want to make a digital circuit to realize this. You see, if I make a straightforward realization, then you require 1, 2, 3 inverters, A bar, B bar, and C bar, 3 NOT gates, 1, 2, 3, 4 AND gates, 4 AND gates, and How many OR? What do you mean 3? Are you sure you require 3? There are OR gates available with more than 2 inputs. So one OR gate should do. Will one AND gate do here? No, because ANDing is coming before OR operation. All right, and it's an expensive circuit. Therefore, we ask, can it be simplified? Well, what we do is, since there is an ABC, we add another ABC. You see how we simplify. We are not going to the truth table. From the truth table, we have found out this. Now, let's see if we can simplify this. We add an ABC. And then, what we do is, we combine these two. Then we get AB, C or C bar 1. Therefore, it is simply AB. And from the rest, we take C common. Then we get A bar B plus AB bar plus AB. All right. And to be able to simplify this now, we add one more AB. This requires a little bit of experience. We add one more AB. Then we say AB plus C. You see, A bar B plus AB is simply B. And AB bar plus AB is simply A. And therefore, this is simply AB plus BC plus CA, which means that you require now one OR gate, no inversion, one OR gate and 3 AND gates. Okay, this is a simplified form. One 3 input OR gate. If you don't have 3 input OR gates, what do you do? 2 input OR gates. Okay. Now there is a mechanization of this simplification, and this mechanization was done by a gentleman by the name Carnot, and we do it with the help of tables which are called Carnot maps. And I shall simply illustrate for this particular example. We are not going to Carnot maps in general, but just to give you a flavor of what a Carnot map is, we go into this example. Carnot map, we once again consider this truth table. We consider the truth table, and what is done is that combinations of AB, possible combinations of AB, are written on the horizontal line. What are the possible combinations? 0, 0, 0, 1, 1, 1, 1, 0. There is a specific reason why we write this. Carnot map must be written with 2 adjacent numbers differing in only 1 bit, not more than 1. You see, we did not write 0, 1, 1, 0 after 0, 1, because that would have meant change in both the bits. This is a discipline that one has to exercise. All right. Consecutive numbers must not have more than 1 bit which is different. 0, 0, 0, 1, only the second bit is different. 0, 1 and 1, 1, only the first bit is different. 1, 1 and 1, 0, only the second bit is different. Okay, these are the possible combinations, and C can be either 0 or 1. Then you draw squares like this. Okay, and you put here the combinations which make the output equal to 1. You see, one of the combinations is AB 0, 1, A 0, B 1, and C 1. So this is a 1. All right. I am talking from the truth table. Truth table says 0, 1, 1 gives 1. So AB is 0, 1 and C is 1. This is a 1. The next one is 1, 0, 1. So 1 0 and 1. So this is 1. All right, 1 0 and 1. The next one is 1 1 0. So 1 1 0. This is 1. Okay, and the fourth one is 1 1 1. That means this one. All others leave empty. All right. Then what one does is one takes two adjacent ones. All right, two adjacent ones. For example, I can take these two, and here there can be sharings. That is, a 1 here can be shared by this as well as this. Therefore, I can have this combination, and finally I can have this combination. This one is shared by this one, and this one. It's something like covalent bonding in semiconductor physics. Okay, it is permitted. But what it illustrates is whatever we did with the help of simplification, it can be done just by looking at it. You see, let's take this this circle, this pair, this pink circle pair. You see, for this C is the material. Whether C is 0 or 1, it doesn't matter. All right, and therefore this pair is represented by simply AB. All right, these two ones are represented by AB because it is 1 1. A is 1, B is 1. All right. If it was 1 0, then we would have A B bar. But since A is 1, B is 1, it is simply AB. This is the pink one. Let me. Okay. The green one, I hope I can find the color. The green one, yes. For this, you see 1 1 1 0. So it is independent of B. B has changed from 1 to 0, but both are 1. And therefore, this is simply AC. All right. And for the black one, finally, for the black one, it is independent of what? A, and therefore this represents BC. And that is all that you have to take care of. You have to pair, and then you get F, the function, as the OR operation of all the three expressions. That is AB plus BC plus CA. And you can show by truth table that this is indeed the majority machine, or the vote taking machine. There are one asks the question, suppose you have two variables. If it is two variables, then it's simpler. Okay, if it is two variables, then you simply write A on this line 0 1 and B in the vertical 0 1. All right, so you shall have 4 circles like this, and then you find out which ones are 1. Try to pair adjacent ones. If there are no pairs, if there is only 1 1, then of course you know what the function is. It's simple. Suppose you have 4 variables. That is, you have, let's say, AB and CD. All right, then I must do it separately. Then you see the AB possibilities are 0 0 0 1, then 1 1 1 0. In a similar manner, 0 0 0 1 1 1 1 0, and you shall have okay. You shall have how many positions? 1 2 3 16 positions. Okay, and from this, from the truth table, you find out which ones are 1, which combinations. For example, 0 1 0 1 0 1. Is it 1? If it is 1, then write 1 here. Now, in such a situation, it may so happen that there are 4 adjacent ones. For example, if we have, let's say, pairs can of course be utilized, but if there are 4 adjacent ones, well, then you enclose them within a curve and look at what it is independent of. This the expression corresponding to this, you see, 0 1 1 1, A has changed. A has changed, therefore it should be independent of A. it should have a B. All right, it's independent of A. Here 0, 1, 1, 1. What has changed? C has changed. Therefore, this simply represents BD. And it's a tremendous simplification. Unfortunately, only up to 4 variables. If it is more than 4, then this square, this map becomes very complicated, and one is not able to minimize. The simplification that we have been doing is technically known as minimization. For more than 4 variables, Carnot map is not used. There are alternative methods for minimization. One of them is, for example, Quinn-McCluskey. Just remember the name, that's all. Quinn-McCluskey, C-L-U-S-K-Y. Quinn was the supervisor of a professor named McCluskey, who is now in Arizona State University, about 80 years old. So Quinn is dead. Quinn was his supervisor. But the method is still very popular. There are many other variations of minimization methods. And I think that is where we shall close this class. Give me a minute, give me a minute, I'll check this. Akshay?